general relativity, step by step. Last time I calculated the Christoffel symbols here for, or at least I calculated all the Christoffel symbols for the polar coordinate system, and I was making the observation that it's a nice symmetrical system, it's a nice flat plane, and we're taking advantage of that flatness in our coordinate system. So we'd expect most of the, or many of the Christoffel symbols to be zero. And they are, because these are the only non-zero ones. So the reason I wanted to do that was because I wanted to solve the geodesic equation, which I've got written down here, x double dots L plus this lot here. So I'm going to write that down and show you how it works in polar coordinates. X double dots L plus Christoffel symbol L, ij, x dot I, x dot j equals 0. So the L index is a free index, so I'm going to put L equals R first, and I get R double dots plus R, and I'm committing a bit of a sin here because I'm mixing x dot j. I'm mixing this index here, which is an R, and I and j are free. In fact, I'll actually write it in, plus sigma over I and j, and that equals 0. So what does that tell us? Well, this is quite complicated because I'm summing over I and j, so I've potentially got 4 terms there. However, there's only one non-zero Christoffel symbol, which is this guy here, gamma r theta theta. So what that tells me is I can ignore everything except I equals theta and j equals theta. So what does that tell me? That tells me that r double dots plus the Christoffel symbol r theta theta is minus r. Theta dot, because I is theta, theta dot again, because j is theta as well, equals 0. So of course that tells me that r double dots equals r theta dot squared. Beautiful, which I'm going to call equation 1. Okay, now that was L equals R, that was that index there being equal to R, and now I'm going to set it equal to theta. So I've got theta double dots plus, and I can do the same trick again, except that I've got 2 non-zero components. So I've got theta r dot theta dot plus theta, and then it's the other way around, theta dot r dot equals 0. And these terms are r to the minus 1. So that says that theta dot dot plus 2 over r dot theta dot equals 0. Yeah. Which I'm going to call, or theta dot dot equals minus 2 over r dot theta dot, which I'm going to call equation 2. Well, that was nice. What I'm going to do is I'm just going to do a very, very light piece of solution for this one. If I've got theta dot dot, I can multiply by r and say it's 2r dot theta dot equals 0, and I can re-express that as d by dt of r squared theta dot. Is that right? Yeah, put an r squared, I'll put another r in here. R equals 0, that's right. Because of course when I differentiate that I get 2r dot theta dot plus r squared theta dot dot equals 0. So this is the first integral of that. And that tells me that r squared theta dot equals a constant. And of course that is representing angular momentum, because it's r omega, I guess, is constant. So it's just representing conservation of angular momentum, which is quite a nice thing. Okay, so we've gone through the geodesic equation here, which looks a little bit formidable, but because we've got such a nice, beautiful, simple system, a nice symmetrical at least system, this polar coordinate system, then that allows us to have a huge number of simplifications, which basically mean that the equations are quite straightforward. And in the next screencast, I'm going to solve these equations and show that they come up with what you expect. Actually, I'm not going to solve them. What I'm going to do is show that they are satisfied by straight lines on a polar coordinate system. So it's a little bit different. Solving them turned out to be a bit harder than I expected. It was a little bit more messy, and certainly not in the keeping with the spirit of this course. So I'm not going to do that. I'm going to do a simple version, which is to show you that straight lines are satisfied. Okay, I'm going to go. Stop.